Okay, kiddos, here we go. This is for all you guys that weren't here Thursday and or Friday or some combination of those days. All right, let's see where I'm going to make this. Let me see if I make this bigger. Go like that. Okay, quick review. Which is a better measure of center, the mean or the median? You're going to get a big lesson quickly, and I'll slow down under the important parts. Let me make my pen bigger. Here's that make it work. Okay, mean or median? Well, I guess it's the same. Okay, which is better? Well, it really depends. The mean is typically what we use for the measure for the center. The problem with the mean is that if I throw in some big outliers or some skew or something like that in my distribution, that gets really that gets affected by it. It gets pulled towards the skew or the outliers, towards the big outliers, whereas the median not so much. And what we've learned in the past is that the median is resistant to outliers, and whereas the mean, what do we know about the mean? Well, I can say the mean isn't resistant to outliers. The mean really is a good measure of center for symmetric data. And the reason I'm pointing this out is because I think maybe in our lessons, I didn't want to give you over the past week this false idea that the mean is just a bad thing and don't ever use it, because it is a good measure of data. We just have to, of the center, we just have to be really careful, because it can be moved a lot by outliers or a bad set of data. So let's just kind of see what can happen with that. We'll look at some examples here in today's lesson. Okay, what about spread? We've talked about IQR, the interquartile range, which, as you know, is Q3 minus Q1. That's the spread of the middle 50% of the data. But something that's more powerful than just looking at the middle 50% of the data is something called the standard deviation. And that takes into account how far each piece of data, every piece of data, is from the mean. Okay? And a question that I'm sure is just popping into your head right now is, well, wait a second. If you're talking about each piece of data from the mean, then that means if there's an outlier, then that's going to be far away, and that's going to make standard deviation very big, and that's bad. And you're right. So this right here, this is only good without, if you have data, oops, let's write it like this, only valid for data sets without outliers. And we also want to use it on data sets where the mean is a good measure of center. And what data sets is the mean a good measure of center? If it doesn't have outliers, and symmetric. Because if it's not symmetric, then it's bad. Oh boy, the battery's running low. Let me grab the power cord. Okay, so we start by figuring out standard deviation by understanding that a deviation is the distance that a data is from the mean. The data value is from the mean. So if a piece of data is x, then a deviation is x minus x bar, because x bar is what we call the mean. So this would be a deviation. Okay, so next. All right. So which one is more spread out? Or are they the same? The first data set, 1, 2, 3, 4, 5, or 1, 1, 3, 5, 5. Now notice the mean is 3 on both of them. So which one is more spread out? Well, this one's more evenly spread out, 1, 2, 3, 4, 5, and this one's kind of like 1, 1, 3, 5, 5. Well, check out what happens if we do this. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. this one looks like this. And this one goes like this. 1, 3, 5, 5. If you look at it graphically, remember, if we're trying to measure, remember, standard deviation is a measure how far data is from the mean. And if that's our measure of spread, how far data is from the mean, this is the mean, then you have to say that this one is more spread out. Okay, from the mean. Okay, this is more evenly spread out, but that's not the our definition of spread. Spread is how far away from the mean is our data. Okay. All right. Consider this data set. We're going to find the standard deviation on here. So we're going to write it vertically, and I'll do it right on this screen here. And we're going to write this as my set. We're going to call it x of I. So x of I represents my data values, x of 1, x of 2, and so forth. X of 1 is 4, x of 2 is 3, x of 2 is 10, 12, 8, 9, 3. And we know x bar, if you calculate that, I believe is 7. Okay. So now what we're going to do is we're going to calculate the deviations. We're going to do x of I minus x bar. Okay, so we're going to subtract my data. X of 1 minus 7 is 4 minus 7, negative 3. 3 minus 7 is negative 4. 10 minus 7 is 3. 12 minus 7 is 5. 8 minus 7 is 1. 9 minus 7 is 2. And 3 minus 7 is negative 4. And so naturally, a question is, well, the standard deviation is a measure of how far from the mean is my data. Well, these are my deviations. This is how far from the mean my data is. So let's just find the average of these. Well, if I add these up, I get negative 7 plus 8 is 1, 2, 4, negative 4. I get 0. Okay, well that doesn't help me because then the average is 0. And that's actually going to happen every single time because of how we define the average by adding the numbers up and dividing by the number. This will always happen. So what we want to do is somehow fix that. And the problem is we've got negatives and positives here. And so what we did, we as mathematicians did a long time ago, is we found it much more convenient to square the numbers rather than take the absolute values. It's nicer to work with mathematically than it is taking the absolute value. So we square the numbers. And so we get 9. These are called squared deviations. And I'm probably off the screen. There we go. Squared deviations. So I get 9, 16, 9, 25, 1, 4, 16. And if I add, now I'm gonna find the average of those guys. So I'm gonna add those up. I get 80. And so I get 80 over here. I'm gonna write it over here. And I'm gonna divide by, there's 1, 2, 3, 4, 5, 6, 7. I'm gonna divide by 7 minus 1, or 6. And I'm gonna explain in a minute why we do that. 80 divided by 6 is actually 13.3. Now let's talk units for a second. If this data set was in feet, for instance, then this is in feet, this is in feet, and these units are now in square feet. So this is 80 square feet. This would be 80 square feet over 6, so this would be square units or square feet. So this is in square units. This is actually what we call the variance. Sorry for squeezing this in on here. And if I want my standard deviation to be in the same units as the original data set, then I'm going to want to, this in square units, I'm going to want to take the square root of that. So then the standard deviation is the square root of 13.3. This is going to be, oops, 13.3, that's 3.65. That is the standard deviation of this data set. And we write that as S sub x for standard deviation, 3.65. Okay. And anything that's more than 2 standard deviations away from the mean is considered an outlier. That's another way of defining an outlier. Remember the other way, when we used the 5-number summary, it was Q3 plus 1.5 the IQR, or Q1 minus 1.5 the IQR for the lower boundary. Now we still have a couple questions we've got to figure out, like, what is this? You know, why aren't we dividing by 7 and things of that nature? Well, let's address that here in a minute. But notice this measure right here, this number, okay, this is only good if the data set is symmetric, without outliers. Okay, because once you have big outliers, I mean, if you have outliers that are close, you know, kind of like this type of thing, and maybe you've got a little outlier out here or here, that's not going to significantly mess it up. But if you've got big outliers, then we're not going to be using the mean anyway. But if the data is fairly symmetric, then it's, you know, we've got some points on both sides or whatnot. If we're using the mean as a measure of center, then standard deviation is a good way to go. It's actually a very good way to measure spread. Okay, let's go to the next book. Here's the formula, and I want to go ahead for the variance. This is just the sum of the squared deviations divided by n minus 1. This is what we call the variance, and we call it s squared. And notice, here's the author, we say, why do we divide by Anderson? In the book it says, hey, we'll show you later. I'm going to show you in a minute here. Standard deviation is s, we take the square root of that. Well, let's just talk about this, and I'm going to talk more than write here. What we do in statistics oftentimes is we want to make inferences about the population. So what I'll do is I will take samples and, you know, and say, for instance, here's my population. Try to look at it like using Venn diagrams. If I want to learn about the population, then oftentimes I'll take a sample and calculate the sample data, and if it's a good representative sample, then I can make that same statement about the population. For instance, heights of high school teenagers, of high school seniors, I should say. I guess all high schoolers are teenagers. But high school seniors, their heights. I could take a good representative sample of 1,000 high school teenagers, high school seniors, sorry, it's getting late, and get an average height of them, and I could say, you know what, this generalizes to the whole population, so I can make a statement about the whole population. That works really well for a lot of variables, in particular for the mean, okay, and for the median it works well, and lots of other things that we're going to talk about later in the course. What it doesn't work well on is it doesn't work well for the standard deviation. If I were to take the standard deviation for a sample, interestingly enough, on average, a standard deviation for a sample is going to be smaller than the standard deviation for the population. Okay? The standard deviation for the sample will be on average. And we'll talk about this more in class, but I want you to kind of have an idea when you look at this, to be a little prepared ahead of time. The standard deviation for the sample will be on average smaller than the population standard deviation. Okay. So the question is, how do we make that bigger? So if I were to do the sample standard deviation, we usually put a little x subscript there, or y in this case up there. If I did the standard deviation like this, x sub I minus x bar squared over n, how would I make this number smaller? Well, I divide by a smaller number. I'm sorry. It'll be smaller. How do I make this number bigger? I divide by a smaller number. So if I divide by a smaller number, that's going to make this fraction a little bit bigger. And interestingly enough, that little bit makes all the difference in the world. It makes this a good, this is now what we call a good estimator for the population standard deviation. And I know there's a lot here that you're just getting a piece of right now on this video, and there's not any give and take. But that's why we divide by n minus 1, because we use this standard deviation as a sample. So every data set that we look at, we're considering it as a sample, not a whole population. Now, if for some reason it says, hey, this is a whole sample, this is a whole population, then yeah, we would divide by n. But we divide by n minus 1 because that's a sample of a whole from the whole population. Alrighty. Okay, so let me just hit some highlights here, and we'll get to the end here. Okay, when data values are tightly clustered around the center, the IQR and standard deviation will be small. When it's far, the IQR and standard deviation will be large. Okay. Now remember SOX to describe distributions. If it's skewed, median and IQR. If it's symmetric, use the mean and standard deviation. This is key right here. Okay, might want to pause it and jot that down. Okay, if the data is symmetric, we report out with the mean and standard deviation for center and spread. If it's skewed, use the median or IQR. Okay, this is obviously thought to be a no-brainer for you right now. And then I guess we got the homework next. Okay, so there you have it. That should do it for you. And sorry I get this up so late, but it's here for you. So I'll talk to you about it in class, and we'll talk to you later. Bye.